Alrighty, here we go in just a second. This is the Smart Buildings Academy podcast with Phil Zito, episode 317. Hey folks, Phil Zito here, and welcome to episode 317 of the Smart Buildings Academy podcast. And in this episode, we are going to be shifting gears from our sales conversation that we've been having the past several weeks. And we are now going to be focusing in on some more technical concepts. So today's episode is going to be making sense of electrical concepts without becoming an electrician. So we're going to be looking at Ohm's law. We're going to be talking about the relationship between current, resistance, and voltage. We're going to talk about why you see the volt amperes drop on transformers as you turn on more devices and turn on more outputs. So we're going to cover a lot of concepts related to electricity. All right. As always, everything can be found at podcast.smartbuildingsacademy.com/317. If you're watching this on the live stream, welcome. Make sure to add your comments as we go through this episode. Make sure to like and subscribe as well. Helps grow the channel. And if you're listening to the podcast, then definitely wherever you're listening to this, add your questions and comments there as well, and we will go and discuss those. Let's dive in. So what do you need to know in regards to electricity? And this is one of the things that, back when I was first starting off in the field, I was trying to figure my kind of place in the field out. I went and applied for an electrical license, and I started the process of pursuing that. I gave up on that because I realized it wasn't necessary. It's kind of where a lot of folks end up. You come into this industry from a variety of different backgrounds. Some folks come from a mechanical background, other folks come from an electrical, some come from an IT, some come from a military background like myself. And really figuring out what you need to know, that is one of the biggest challenges. As if you talk to someone with an electrical background, they're going to say, hey, you really need to understand all of this electrical stuff because they lean on that. But you may not need to know all that stuff. And then if you go under someone with a mechanical background, they're going to tell you, hey, pursue an apprenticeship, really become a mechanic, understand the systems first. And in reality, I've never changed a compressor in almost 20 years now. And I'll tell you that a lot of what you would learn that path is unnecessary. So the purpose of this episode is to really explore some key concepts and understand how all this ties together. I will do my best to take a visual concept and turn it into audio. For those of you who are listening to the podcast, do realize that at podcast.smartbuildingsacademy.com/317, there will be a video accompanying this as well. Alrighty, let me grab my little pen wherever it is around here. It is somewhere around here. And we will get started. There it is, over there. All right, I'm going to switch us over to the whiteboard. Just let me turn it on, and we will get started going through some electrical concepts and talking through all sorts of fun things like the Ohm's law. All right, 1 second here. There we go. Switch audio around. Switch the camera feed. There we go. Camera feed. Okay. Switch over our audio. Audio should be switched. And there we go. As far as Ohm's law goes. Let me step over here. Okay, everyone's seeing that? Good to go. Alrighty. Let me clear off this. This was from my workforce development stuff yesterday. Okay, so you all should be hearing me now. I'm just going to verify that sound is good. Yep, sounds good. Okay, perfect. Alrighty. So continuing on this electrical concept, you've got Ohm's law, right? Volts, current, resistance. These come together to form what is known as Ohm's law. We'll talk about the relationship here in regards to how this all works. But what we have to understand, in a traditional building automation system, we have a transformer. And this transformer, quite simply, transforms power. Typically, it's what's called a step-down transformer. And it's going to typically step down voltage, typically 120 volts AC, and it's going to step that down to 24 volts AC. And in the process, this transformer is going to have what we know as VAs, or volt amperes. So one of the things I first want to talk about here with Ohm's law and just electrical concepts in general is you have volts, that's one measurement, right? Volts, electrons flowing across the wire. You have I, which is is current, which is known in the term of amps. And then you have R, which is known in the term of ohms, which is resistance. So volt amperes is quite simply the ability to transfer this power from the transformer to the end device. Now, what does that look like? So we have a transformer, and our transformer has on the secondary side. So you have a primary side, which is the incoming power to the transformer, especially with a step-down transformer. And then you have the secondary side, which is where we're primarily concerned as controls folks. And this secondary side is where we have our 24 volts AC. And typically we'll have transformers that are rated like for 40 VA or 100 VA, etc., right? And what happens is as this transformer goes and feeds a controller, oops, I dropped my pen. This thing's so small. I need a bigger pen. So as this transformer feeds to this controller, this building automation controller so the transformer feeds from the secondary side to the controller, then this controller is going to have potentially internally sourced voltage. And this voltage is potentially used to drive devices. So you'll see where controllers have internally sourced voltage to drive what are known as coils, more on that later. And you'll also see where transformers go directly to the control device, like maybe an actuator, and they actually enable the motor of the actuator to be driven. Now, what happens is that whenever you are going and using a transformer, so you're using a transformer, and this transformer is going to a resistive load. A motor impedes the transfer of electrons. So what happens is electrons, volts, are the power, and this transformer is providing that power. And what happens is when that power hits this device, it starts to impede the flow of the electrons. And since volt amperes, VA, is current times volts, obviously the electrons decrease and our VA is going to decrease. The capacity of the transformer to provide that power to drive devices is going to decrease as we activate more devices off this secondary. So I'm going to just check, see if there's any questions on that real quick in the chat. Just taking a look here, making sure that it's still coming through good as well. All right, we're looking good. No questions so far. That's awesome. I know this is kind of weird for a podcast / video, but I'm trying to make it do both audio and video at the same time. So you've got this one concept right here where this load, this actuated load, goes and causes the transformer to have less VA, to have less power to be able to then go and drive devices. Now, what's happening is you will see that on a transformer or on a controller, like if we were to bring up a controller catalog sheet, what would happen is the controller catalog sheet would say an unloaded controller maybe requires 14 VA, but requires 40 VA when it's fully loaded. That's because the controller is sourcing voltage to drive outputs, and as it drives outputs, those outputs have certain amp ratings and voltage ratings, which then decrease the VA capacity of the transformer. So to put that in another way is if you've ever used a garden hose and you've interrupted that, or not a garden hose, a drip hose to do a garden, and you've run water to that drip hose. And as you go from drip nozzle to drip nozzle to drip nozzle, the pressure gradually reduces to the point where you go from a potentially strong drip to a very weak drip further down that drip hose line. Well, that's the same concept of a transformer and decreasing VA. As you put more resistive loads onto that circuit, then we are going to see a decrease in power ability to the point where it can get so low that devices cannot fully actuate, or in a worst case scenario, controllers actually start to go online and offline. That's why sizing your transformers for a accurate VA loading is critically important. So far, right, we've covered these concepts of a transformer. We've talked about VA. We've talked about Ohm's law and somewhat the relationship between these things. So if I were to blow out Ohm's law even more onto the screen, you would see that how it works is kind of like this. And what I'm drawing is a V at the top with dividers for both current and resistance. So current times resistance, right, is going to equal voltage. But if I want to get voltage, then, or sorry, it's going to equal voltage. If I want to get current, then what I am going to do is I'm actually going to divide voltage by resistance, and that's going to equal current. And so that's kind of how all of this comes together, is this equation works. You know, as you have one variable to solve, you have one variable, you can go and solve the other variables. Or sorry, if you have two variables, you can go solve the one variable. Gotta love math. I hate math. Any of you who have followed this podcast for any amount of time know that I hate math. All right, so continuing along this concept of voltage, current, and resistance. On a circuit, we have what is called a circuit, and we typically use circuits extensively in building automation. And what we use circuits to do typically is we will go energize coils, and we will use these coils to change the states of contacts. This is a very, very common approach to a lot of building automation problems. You want to turn on a fan, we go energize a relay coil, and we allow voltage to pass through the contacts, and those contacts will energize a starter or energize a motor, etc. So what I'm drawing on the screen right here is a circuit with a circle on it, which is a coil. And that coil gets energized, and when that coil gets energized, it changes the state of the contacts, which are these metal contacts basically, and they open and close based on the energization of this coil. And as those contacts change state, they either create a complete circuit to allow voltage to pass through, or they don't. So what we would have is maybe something like what I'm drawing on the screen is a normally open set of contacts. And as a coil gets energized, that normally set of contacts, or normally open set of contacts, closes. And then we have hot and ground as a circuit. And somewhere in between, this, we will have a device, maybe like a starter. And that starter will get energized. And as that starter gets energized, that then allows a fan to turn on. Now, to pull in that coil requires a certain amount of amperage. To go and energize starters directly requires even more amperage, and that's where some of this VA loading concepts comes from. So this is a key concept that you need to understand in building automation. So in building automation, we need to understand circuits, we need to understand coils, we need to understand closed and open contacts, transformers, secondaries, primaries, and the effect of resistive loads on the secondary from a VA power perspective. So a lot of concepts swirling around. And I'll point you to some resources we have at podcast.smartbuildingsacademy.com/317. Oh my gosh. If you want to dive deeper into this, I'm just going to see if there's any questions so far, because I know this is a technical topic. And I'm going to see how this is flowing so far with folks. Excuse me. Alrighty. Continuing along with this episode. So we've talked about Ohm's Law, we've talked about VA, we've talked about transformers, we've talked about circuits. Now let's talk a little bit about input and output types and how those exist from an electrical perspective. So on the input side, we will typically have resistive, digital, volt DC, milliamp, and pulse, which I'm not really going to talk about too much, as our input types. And each one of these input types requires different wiring approaches in order for them to operate. So a resistive element, quite simply, you just complete a circuit with the resistive element in the middle of it, and that resistive element, whether it's like a 1K nickel or a 10K type 2 or type 3 thermistor, those are going to go and sense temperature typically. Digital is typically a on-off state. So this would be something like a contact closure where you are either sensing resistance or you're sending a 5-volt DC signal through this contact closure. And as you sense that signal, the controller knows that the state has changed from either on, off, open, shut, etc. These are used for end switches, like on actuators, end switches on dampers. These are used for like fan status with flow switches. These are also used as auxiliary inputs from safeties, like low temp safeties, etc. Volts DC, this is another one that's pretty straightforward. It is polarity sensitive, which we haven't talked about yet, but we'll talk about in a second. But it's very similar in that you route one side of the inputs to the input side and the other side of the input to the common side. And you may have to power this sensor externally with an external transformer. Sometimes the controllers actually have their own power. And milliamp is very similar in that you go and pretty much wire it up the same. There is a little bit of nuance on some controllers that involves resistors, that involves doing things a little differently, but for the most part, it's wired up the same as well as it's sourced. How you measure volts DC and milliamp is a little different. Because volt DC, you can simply measure across the contacts and you can be like, okay, this is 5 volts. Whereas with milliamp, you either need an amp clamp to detect that amperage, that heat, that current, or you need to measure that current, what is called in series. So volts DC, you can measure in parallel. You can put your leads across the wires, your multimeter leads, and you can call it a day and measure it. Milliamps, you either have to have an amp clamp to go and sense the current, or you have to measure what is called in series. So you have to interrupt the wire and actually put your leads in between one side of the wire to the other side of the wire to detect that that current. On the output side, we have 3 primary outputs. We have voltage, which is either internally sourced or externally sourced. This is typically 24 volts AC, although it can be 120. You don't typically route that through a controller though. And that is going to enable those coils that I mentioned earlier. It's going to energize those coils to go and affect those contact closures. You have volts DC output. This is commonly used for a proportional valve actuator or for like a VFD control signal. It's typically 0 to 10 volts DC, polarity sensitive, which I'll talk about in just a second. Used to drive VFDs, used to basically give a proportional, a variable control signal to drive a device. And then you have milliamps. The big difference between volts DC and milliamps is that with volts DC, those tend to be shorter runs that are not prone to electrical interference. Milliamp, tend to work well with longer runs that are potentially subject to interference. That's because current, right? If we go back to Ohm's law, current is created by voltage divided by resistance, whereas voltage is created by current times resistance. So as we have that resistive effect, we are going to see more and more that we have some issues with our volts. And we're also going to have signal degradation from just noise in general over a longer distance. All right. I always second guess myself whenever I'm doing Ohm's law equations. I'm like, was it volts equals I times R? Or was it divided? I always mix that up no matter how many times I've taught it. Man, it's just kind of one of those things that I'm always self-conscious about. So I mentioned polarity. And when we're using volts AC, we're using what's called alternating current. And if you think about a battery has a positive and a negative side on it, right? I just drew a negative as a vertical line. There's a horizontal line for a negative. So what happens is the electrical, in the case of AC, it alternates between positive and negative. And so it's called alternating current. So if you were to plug in an AC circuit, it's what's known as polarity insensitive, meaning if you hook up the positive side to the negative side or the negative side to the positive side, it's not really going to matter. Whereas if we use direct current, we are doing a direct current, which is going to look more like a block on a not multimeter, oh my gosh, oscilloscope. And what will happen is our positive will be positive and our negative will be negative. And if we cross those wires, we are going to cause the signal to basically be inaccurate and improperly controlled and cause all sorts of issues. So we need to be cognizant of the polarity sensitivity of volt DC wiring. Okay, so this point we've covered Ohm's law, we've covered input and output types, we've covered circuits, we've covered polarity sensitivity, and we've covered transformers and secondaries and how loading on the secondary reduces the power capabilities of that secondary to transfer power to whatever devices we're doing. I'm going to take a look and see if there's any questions so far. All righty. Perfect. So continuing right along, the last thing that I will leave you with here in regards to this electrical concepts is going to be just a little tidbit in regards to controllers and amperage. Excuse me. So on inputs and outputs, controllers have amperage ratings. And remember, amperage is heat, amperage is current. And if we have too much amperage, we can damage our internal components to our controllers. So we need to be cognizant of the amperage ratings of our inputs and outputs when we attach devices to them on the controller so that we don't damage the controller. This becomes specifically important when we are using externally sourced power and routing that through our controller output. So if we have a relay output inside our controller and that relay opens and shuts inside our controller, then we need to be cognizant of the amperage rating for that output so that we don't go and put too much amperage through that output. That can cause the controller to be damaged, sometimes permanently, and that can just be a very bad thing. So there you have it, some electrical concepts. This is by no means a sweeping electrical course, but this should give you some understanding of baseline terminologies. If you do want to dive deeper into these electrical concepts, we have a much more formatted and structured course on wiring and installation of control systems, inputs and outputs. You can check that out at podcast.smartbuildingsacademy.com/317. We'll have a link to that. And as always, if you have any questions, please do not hesitate to ask. I'd love to answer your questions. And thank you so much for being here. I will see you in the next episode. Take care.